In this section, we're going to be looking at functions, and we'll actually be looking at functions for quite a bit of the remainder of this course. The definition of a function is a relationship between two variables where each input value is assigned exactly one output value. Now, there are lots of different ways to write functions. We're going to look at a couple of them here. One way to write a function is to give the values in a table. So I'm going to give you one thing that is a function and one thing that isn't a function. Here's a function. The inputs, the x's, are 1, 2, 3, and 4. And the outputs are maybe 8, -7, 4, and -7. There's a function. That's a function because every input value has a unique output value. If I give you the input x equals 1, there's only one output value you can give me, 8. Similarly, if I give you x is 4, there's only one output value you can give me, -7. Now, notice that -7 does repeat as a y value. That's okay, because the rule for a function said every input has one output. It does not say that every output also only has one input. Alright, so let me give you an example of something that's not a function. Again, I'm going to build a little table here. 1, 2, 3, 1. 0, 4, -2, 6. Alright, this one is not a function. Why is this one not a function? Because x equals 1 repeats. If I give you the input x equals 1, you would have to give me two answers for the output. You would have to tell me y is 0 or y is 6. Okay, so there's one way that we represent functions. We represent functions as tables. I could just as well write all of these as ordered pairs. For example, this first function here, instead of building a table, I could write ordered pairs for each of these points. So functions can be represented by tables. They can also be represented by ordered pairs. But for the most part in this course, the way we're going to represent functions with equations. So let me give you a couple of equations. One equation will be a function. One of them will not be a function. Here's an equation. Y equals x squared minus 2x. This one happens to be a function. Why is it a function? Well, the main reason is, again, if you start to build a little table here, pick any number that you like for x. Just for fun, I'm going to pick -3. If I take -3 and plug it in for x, how many answers do I get? If it's a function, I'll only get one answer. If it's not a function, I'll get multiple answers. Well, if I plug -3 in, -3 squared is 9 plus 6, because I got a double negative there, that's 15. So if I plug a number in, if I plug in -3, I only get one answer. What if I pick a different number? What if I plug in 1? Again, how many answers would I get? If I plug in 1, I would get 1 minus 2, that's -1. Alright, so this equation is a function. Now let me give you a different equation. X squared plus y squared equals 10. Turns out this one is not a function. Why not? Well, again, I'm going to build a little table here, and I'm going to pick my favorite number for x. I'm going to pick 1 this time. If I pick 1, I get 1 plus y squared equals 10. That's the same as y squared equals 9. Now, a lot of students would make a mistake here. They would tell me y has to be 3, which is halfway correct. Or, the answer they tend to miss is y could be -3. Because -3 times -3 is also 9. So this one's not a function. It's not a function because for the input x equals 1, I ended up with 2 outputs. Not a function. So what's the difference between these two equations? Well, if you have an equation, you can generally pretty quickly tell if that equation gives you a function if you can get y all by itself. if you can get y all by itself and not have to do a square root on both sides. So there's your problem right there. The problem for this one right here is that y squared. In order to get the y all by itself, I could get the y all by itself, but I'd have to do a y squared on both sides, or a square root of y on both sides. When I square root on both sides, I need to remember that there's a positive one, like the positive 3, and a negative one, like the negative 3. Alright, the other way that we're going to represent functions in this class is with graphs. And once again, it's very easy to tell from a graph if something is a function or not. We use something called the vertical line test, which I like to abbreviate BVL because vertical line test takes too long to write all out. Alright, so I'm going to give you a couple graphs here. So here's a graph. Some sort of third degree polynomial it looks like, I'm not sure. But here's how the vertical line test works. If I draw a vertical line anywhere, how many times does it hit the graph? It only hits it once. And it really doesn't matter where I draw that vertical line will only cross the graph once. If that happens, then you do indeed have a function. Let me give you a different graph here. How about this one? Kind of the same shape, just turned on its side. This one is not a function. And the reason it's not a function is it fails the vertical line test. And what I mean by that is I can draw a vertical line right there. Well, it's supposed to be a straight vertical line. It hits the graph more than once. Why does that make it not a function? Well, the reason it makes it not a function is look what we have. This right here, this first intersection point, that looks like it's about 3, 7. And this one here looks like it's 3, 3. And this one down here, this one happens to hit 3 times, it's 3, -6. So what's happening is I have an x value of 3, an input, used more than once. So that's how the vertical line test works. If you have a graph, you simply draw vertical lines. If any vertical line anywhere hits more than once, then your graph is not a function. Conversely, if all the vertical lines you can draw hit only one time, then you do have a function. Alright, the next thing we have in this section that we're going to use a lot in this course is called function notation. Alright, so we're very comfortable with writing functions this way. I might give you y equals x squared plus 2x minus 3. Conversely, I might write that in function notation. In function notation, I would write it this way. F of x equals x squared minus 2x plus 3. Those two things really say the exact same thing. I have a function. Over here, on the left-hand side, I called my function y. On the right-hand side, I use this symbol f parenthesis x. That right-hand side is a little bit more descriptive. What that says is my function name, I'm going to call my function f. So f is the function name, and the parenthesis x tells you x is our independent variable. X is our inputs. Okay, so what we've done quite often, over on this left-hand side, we've done this already quite a bit in this course, is we've built little tables, and we might say x is, I'm just going to pick a number here, 2. And then we would figure out the y. We would write y is 4 plus 4 minus 3, that's 5. And then we make another line in our table, let's say x equals -1. If x equals -1, I would have 1 minus 2 minus 3, that's minus 4. I can write the exact same thing using function notation. It would look like this. I would write f parenthesis 2. Notice that x got replaced with the number 2 on the left-hand side. All that means to do is replace x with the number 2 on the right-hand side. So I would write 4, whoops, got the function down wrong, didn't I? It should be x squared plus 2x minus 3 to make it the same as the over there on the left. So I plug 2 in, I get 4 plus 4 minus 3, I still get 5. And then I can write f parenthesis negative 1. That simply means x is negative 1. Plug in the negative 1, I get 1 minus 2 minus 3. It's still minus 4. Okay, so function notation is kind of a shorthand way of writing the exact same thing and building these tables. And function notation will be very important for us later on in this course. Later on in this course, we'll be dealing with multiple functions, and it's handy to call them f and g and be able to distinguish them. And this notation is extremely important when you get into calculus. We'll use this notation for functions all the time in calculus. We'll almost never use the y notation. All right, I want to do a few more. I'm going to make up a new function here. F of x is x squared minus 3x plus 5. And again, I might give you f at 4. And again, all that symbol means is you don't write the letter x anymore, you write the number 4. So you simplify that, you've got 16 minus 12, that's 4, 4 plus 5 is 9. Or I might write this symbol, f at z. That really doesn't mean anything. All it means is I've decided for some reason I don't like the letter x anymore. Instead of the letter x, I want to write the letter z. Or one that we're going to see a lot in this course, and we'll see it a lot in calculus for a very important reason. We might write f of x plus h. Now, a lot of students get this very confused. And I understand the confusion. The confusion is these parentheses right here, they look a lot like multiply. But when we're dealing with function notation, those don't mean multiply, they mean plug in. So this symbol means, go back to my original function. Here's my original function. Don't write x anymore. Wherever you see an x, write x plus h. So I write x plus h, and then I have to square it. Minus 3. X plus h plus 5. Okay, so you need to get used to that. When you're dealing with functions, this parenthesis symbol doesn't mean multiply, it simply means plug in. Alright, the last thing we have in this section is domain and range. Domain is all valid inputs. And range is the opposite, all valid outputs. Alright, sometimes when we talk about domain and range, we talk about them from pictures. So I'm going to draw a picture here. Here's a graph. And I might ask you, what's the domain of this function? What's the range? Domain. Domain means the inputs. Domain means the x numbers. So for this graph, when I'm talking about domain, I want to know how far left does it go and how far right does it go. Well, these arrows here on the end indicate to me that this graph goes forever. So this graph goes on the left-hand side, it goes to the left forever and keeps going up forever. And on the right-hand side, it goes to the right forever and keeps going up forever. So our domain, it goes all the way to the left forever, all the way to the right forever, would be all real numbers. Which I would write that way. The range, on the other hand, means all the y numbers. Now, what I notice is that this graph has a low point. It's got a low point right there. That's the lowest point on this graph, and then the graph goes up. So the domain here is not all real numbers. The graph never goes below -6. So my range here, I would write y greater than or equal to negative 6. Negative 6 is my lowest y number, and then the graph goes up forever. All right, let me draw another picture here. How about this function? This is some weird function. Not sure what it is. Don't know what kind of equation it would come from, but there it is. There's a function. It's a function. Why is it a function? Passes the vertical line test. Anywhere I draw a vertical line, it only hits the graph once. Now, what's the domain? Well, how far left does the graph go? The furthest left point is right here, and the furthest right point is right there. And it does hit all the points in between. So our domain looks like it's negative 10, less than or equal to x, less than or equal to 7. That's as far left and as far right as this graph goes. How about our range? Our range, we're looking for the lowest value, there's the lowest value, to the highest value. So our range looks like it has a low of, looks like negative 7, and a high of 5. So there would be our domain and range for that function. Alright, now the last thing in this section. Sometimes I'm just going to give you equations, and I'm going to ask you for the domain. I won't usually ask you for the range if I give you just an equation, although I could. Finding the range is usually a little bit difficult. In order to find the range, generally what you do is you draw a graph, and you look at the graph. So I'm just going to ask you for the domain here. The domain means what numbers can you plug in for x? Well, looks to me as though I can plug in any number for x. For that one, all real numbers. Because I can plug in any number. I can take any number and multiply it by 2, and then subtract 3. Alright, so that one was an easy one. How about this one? This one's a little harder. Alright, what's the domain on g of x? Well, g of x has an issue. The domain is not all real numbers this time. The domain, I think, is all real numbers, except x cannot equal the number 2. X can't equal the number 2. If x equals the number 2, I end up with 0 on bottom. And I can never have 0 on bottom. So, when I give you a function, that's one of the things you need to be concerned about when you're looking at domain. If you have a fraction, you can't have 0 on bottom. Now, this is sometimes written this way, too. Negative infinity less than x less than 2, 2 less than x less than infinity. I think it's a hard way to write it, so I don't write it that way. I would just write x is not the number 2. Alright, my last function, h of x is the square root of x minus 3. When I give you domains and I give you functions, this is the other kind of thing you need to worry about. You need to worry about fractions like we did in g, but for h you need to worry about your square root. And here's the problem with square roots. You can't have negative numbers underneath your square roots. So for this one, my domain, I need to make sure I'm dealing with no negative numbers, which means I need to have x minus 3 greater than or equal to 0. I can't have negatives under that square root. So my domain here, I would get x all by itself. X is greater than or equal to 3.